if you've taken Algebra 2, you're somewhat familiar with the difference of squares rule. X squared minus y squared is the same as x plus y times x minus y. And I want to point out some uses of this that aren't obvious and how it fits in to the rounds here. Let's start with an example with pure arithmetic. Rebecca, could you give me a number in the 30s?
32.
32 times 28. How quickly can you calculate 32 times 28? It is 896. Here's how. This is 2 more than 30. This is 2 less than 30. So in a way, this is 30 plus 2, and this is 30 minus 2. And 30 plus 2 times 30 minus 2 is the same as 30 squared minus 2 squared. That's 900 minus 4, which is 896. And it's done! Have you ever noticed that whenever you have a perfect square on the multiplication table, let's say 7 times 7, which is 49, and then you move 2 places diagonally across, and you end up with 9 times 5, which is 45, that's always exactly 4 less than the perfect square? That's because you add 2 to one of them, subtract 2 from the other of them, and that is going to be 2 squared less than whatever the perfect square was. If you go 3 spots diagonally, it'll change by 9. 10 times 4 is 9 less than 49. If you go 5 spots over, if you keep going, it'll be the square of that gets subtracted from it, which is why I did this so easily, because it was 2 more than 30, 2 less than 30, so 30 times 30 minus 2 times 2. Rebecca, give me a number in the 40s.
43.
Oh, bigger.
49.
43 was too easy. 49, great. Times 31. Great, so those are 9 more than 40, 9 less than 40. That'd be 40 times 40 minus 9 times 9. And it's 1519 is that. So difference of squares is a really useful tool that helps me do arithmetic, and then I get to impress all my freshman students because they're all like, oh, Mr. B, you can do arithmetic so fast. And I don't know how I'm cheating and just how many years of practice I've got. But yeah.
So many.
So many years of practice. Yeah. Since I was very, very young. Okay, so I want to point out how this has uses in the most recent 2015-2016 third question of the round. Here was the thing. They wanted you to calculate the solutions to this. Now you may be thinking, that's not a difference of squares, that's a sum of squares. But wait. Now it's the difference of squares. Over here. And one of the interesting things about the math team stuff is that you just have to find new clever ways of applying stuff you already know. And if you think clever, you can often outdo think straightforward. And, key point in this specific problem, we're used to seeing simple things squared. We're not used to seeing complicated things squared. So, complicated things squared. Looks a little like Pythagoras, huh? Coincidence? Maybe, I don't know. But over here, I can then do this plus this times this minus this. And the thing is that otherwise there's a lot more to distribute. And if I do it this way, I've got 8x minus 1 times, 2x plus 3 equals that, and I can distribute, it can avoid me a lot of the distribution. 16x squared plus 22x minus 3 equals, let me wall this off, 2x you know what? You guys might well have done it more easily the original way because you're fairly practiced in doing perfect squares. But I want to present this as an alternative because you never know when it comes out in handy. And maybe I'll discover at the end of this problem that I was onto something. Oops, that isn't right. No, that is right. Good. Oh look, 6x, 1, x, 2. Did I do the signs wrong? I might have done the signs wrong. Oh well, whatever. I don't really care enough. Yeah, I really don't care enough, huh? Yeah, maybe you have to use the formula, maybe I made an arithmetic error. I don't care enough, it's just an example. My point is that you never know how perfect squares and difference of squares might come in handy here. In general, you won't have to use the formula, so I probably made a math error somewhere. Oh well.